Hello and welcome. This is video 1 of 4 for Deep Learning Unit 3. This video opens the anti-overfitting toolbox, the L1 and L2 penalties, lasso and ridge, and the elegant theory beneath them, penalties as constraints, the Lagrangian, and why deep networks desperately need regularization at all. We end with the classic L1 versus L2 quiz. Let's open the toolbox. Hello everyone and welcome to Unit 3, the Practitioner's Unit. Unit 2 ended with a network that trains. This unit is about training at WELL. The first half is the complete anti-overfitting toolbox regularization, L1 and L2 penalties, dropout, early stopping, data augmentation, ensembles, even defending against adversarial attacks. The second half is the optimization machinery, why deep training is hard, how to initialize weights properly, and the adaptive optimizers, ending with Adam, the default optimizer of the modern world. By the end, the magic incantation you see in every tutorial, Adam, with he initialization and dropout, will be 3 ideas you deeply understand. Let's begin. The roadmap to dense parts. Part 1: regularization, the L1 and L2 penalties, the constrained optimization view with the Lagrangian, data augmentation and noise injection, semi-supervised and multitask learning, parameter sharing, sparse representations, ensembles, bagging, boosting, stacking, dropout, adversarial training, and the tangent methods. Part 2: optimization, training as pure optimization, the 4 hazards of the loss landscape, initialization strategies, zero random, Xavier, he, and adaptive learning rates from Adagrad to Adam. It's a toolbox unit, lots of tools, each with a specific job. I'll give you a filing system on the way in. Your capabilities by the end of this unit. You'll write and explain the L1 and L2 regularized losses and predict their opposite effects on the weights. You'll connect penalties to constraints through the Lagrangian and explain the multiplier alpha. You'll apply the practical toolbox, dropout, early stopping, augmentation, ensembles, knowing what each one actually does. You'll design multitask networks with hard or soft sharing. You'll explain adversarial examples and the FGSM formula. And you'll choose initialization schemes and optimizers with justification, not just because the tutorial said so. My study tip for this unit: make 1 flashcard per technique, what it does, its formula if any, when to use it. The quizzes test exactly that. Part 1: regularization for deep learning. Here's the definition to write down, straight from the textbook. Regularization is ANY modification to a learning algorithm intended to reduce its test error but not its training error. Read that twice, it's subtle. We deliberately make training performance worse or unchanged to make real-world performance better. And your filing system for the 15 or so techniques ahead: 4 buckets. Penalty methods change the LOSS, data methods change the data, architecture methods change the NETWRK, and procedure methods change the training process. Every slide in this part drops into one of those buckets. Let's open the toolbox. Why does deep learning need regularization so badly? Because of a superpower that's also a curse. Recall Unit 2: overfitting, brilliant on training data, useless on new data. Now here's the deep learning twist: modern networks are so flexible they can reach training error of essentially 0 without learning the true pattern at all. They can literally memorize the entire dataset, noise, errors, everything. Think about GPT scale models, billions of parameters. They could memorize their training text verbatim. The reason they generalize instead. The techniques in this chapter: weight decay, dropout, early stopping, working together as discipline. The 2 classics: we start with lasso, the L1 penalty, and ridge, the L2. Both change the loss function, which is bucket 1 of our filing system. Technique 1: L1 regularization, lasso. The name literally spells its job: least, absolute shrinkage and selection operator. The mechanism: add to the loss the SUMOF, absolute values of all the weights, scaled by lambda. Now large weights literally cost the model, so at every training step, the optimizer shrinks them. And here's L1's signature magic: some weights become exactly 0. Not small 0. Those neurons and features switch off entirely. The result is a sparse model and automatic feature selection for free. Why exact zeros? The absolute value penalty pushes with constant force all the way down. It never eases off as the weight gets small. Remember Unit 1's L1 normandy sparsity story. Same mathematics, new job. Practical case, 1,000 input features, most of them irrelevant. L1 finds and zeros the useless ones while training. Lambda a small number like 0.01 sets how aggressively. Technique 2 L2 regularization ridge regression, known in deep learning as weight decay. The mechanism penalized the squares of the weights instead of their absolute values. Squaring punishes big weights disproportionately. One huge weight costs far more than many small ones. The result, and here's the contrast with L1 that examiners adore, weights shrink smoothly toward zero, but rarely reach exactly zero. L1 gives sparsity and exact zeros. L2 gives small evenly distributed weights, smoother functions, better generalization. Why does L2 stop short or zero? Because the squared penalties pull weakens as the weight approaches zero. The gradient of W squared vanishes at zero. L1's pull never weakens. Two personalities from one exponent. And lambda is a dial, at zero, no regularization overfit risk. Cranked huge, all weights crush underfitting. Where's it tuned? On the validation set, because lambda is a hyperparameter. Unit 2 everywhere. Now a change of perspective that unlocks the theory. Penalties are constraints in disguise. The penalty view which we've been using minimized the loss plus alpha times omega of theta, pay a price for large weights. The constraint view forget prices impose RULE. The norm of the weights must stay below some limit k, stay inside the ball, period. The claim on this slide, these two views are equivalent, the same problem, worn two ways. The soft version charges you per unit or size, the hard version draws a boundary. My favorite analogy, speeding. A per kilometer per hour fine, that's the penalty view. A hard speed limit with instant enforcement, that's the constraint. Both keep you slow. And notice where we've landed. Minimizing subject to a norm ball constraint is exactly Unit 1's constraint optimization. The bridge between the views is the Lagrangian. Next slide. The Lagrangian and the starring role of the multiplier alpha. To solve minimize J subject to the weights staying under limit k, we build one combined function, the Lagrangian. J of theta plus alpha times the constraint violation, omega minus k. Now watch alpha work in two cases. Case 1, the weights grow too large. Beyond k the violation term goes positive, the optimizer increases alpha and a strong penalty force pushes the weights back down. Enforcement, exactly when needed. Case 2, the weights are already small, inside the limit. No violation, alpha stays small and no unnecessary shrinking happens. So alpha is an automatic controller. I think of it as a thermostat. Drift from the set point and the system pushes back hard, sit at the set point and it idles. And yes, this is Unit 1's KKT machinery, with its multipliers and complementary slackness doing a real job in deep learning theory, cashing its check. So if penalties and constraints are equivalent, why would you ever prefer the explicit constraint? Two solid reasons. Reason 1, avoiding dead neurons. A very large penalty can crush weights to nearly zero, and a neuron with near zero weights produces near zero outputs and near zero gradients. It stops learning and never recovers. A constraint doesn't crush anything, it only caps how large weights can get. Live neurons, bounded weights. Reason 2, training stability. With large learning rates, weights and gradients can feed each other into a blow up, the numerical explosions, or Unit 1. The constraint prevents this by projecting the weights back into the allowed region whenever they escape. And that projection is literally Unit 1's projected gradient descent, the dog on the leash applied to the weights, every step. In practice this is called max norm regularization, and it famously partners with dropout. Everything connects. One more piece of theory, and it's the philosophical heart of the whole chapter. Under constrained problems. A problem is under constraint when the model has too many parameters, and the data has too little information to pin them down. A million weights, 10,000 examples, the model has enormous freedom. The toy picture, draw this yourself. Two data points on a page. Now draw a curve through both. A straight line works. A parabola works. A wild zigzag works. Infinitely many curves, all fitting perfectly. The data cannot choose between them. The solution is not unique. Deep networks live in this situation. By design they reach training error zero along countless different paths. Without regularization, weights balloon, the model memorizes answers, test performance dies. With regularization, we add the missing rule. Among all the perfect fits, prefer the simplest. Regularization isn't a patch on learning. It's what makes the learning problem well posed at all. Quiz 1: the L1 versus L2 showdown. You need a model that automatically ignores irrelevant input features by driving their weights to exactly zero. Which regularizer does this and why? A. L2 ridge squaring makes small weights vanish. B. L1 lasso, the absolute value penalty pushes weights to exactly zero, giving sparse models. C. Early stopping halting training zeros unused weights. D. Dropout dropped neurons keep weight zero permanently. Think about which penalty keeps pushing all the way to zero and which one eases off. Pause and choose. The answer is B. L1 lasso. The absolute value penalty has constant slope, so it pushes small weights all the way to exactly zero. Sparse models automatic feature selection. That's the selection operator in lasso's name. L2 option A gets weights small but almost never exactly zero. Its pull weakens near zero. Early stopping option C freezes weights wherever they are, not at zero. And dropout option D is the subtle trap, it zeroes activations temporarily during training. The weights themselves survive and return at test time. If you fell for D, perfect timing, because dropout's real mechanics are coming later this unit. Follow up to ponder: when would you prefer L2ing? When all features carry some signal, and you want smooth small weights rather than a hard selection. If this lecture helped you, do like, share and subscribe to Shri Tech Bytes for more lectures like this one. See you in the next video.